All right, so today we'll finally talk about linear regression. For today, the things that we're going to talk about, what is a linear regression? We're also going to go about fitting a regression. And again, I'm sure some of you have seen this table, especially those of you who saw the presentation from my other cohort. We're going to go through this table, what all of these numbers mean. We're going to look at predictive power of a model and some overall assumptions. Lots of things to go through. Hopefully, most of you have already seen some of this material, so we'll be a little bit less intense. But let's get started. So, introduction to linear regression is actually part of statistical learning theory. Statistical learning theory, this phrase, not super important to remember what this is, but if anyone ever brings up statistical learning theory, that's what it is. The main idea of statistical learning is we're constructing a model to draw certain conclusions from data and also to use a model to make predictions. Over the course of this study group, we'll talk about how we can draw conclusions about our data from our model and also how we can use this model to make predictions. There's also a really, really good textbook that actually goes really well with this course. A lot of the things we're talking about go hand in hand with the chapters. I'm going to send that out after this study group. It does go a little bit too in depth for being able to digest everything with the pace we're going at, but very, very good for future reference. If you ever want to take deep dives into any algorithms that we talk about, that's a really, really good book. So I'm going to send that out later on. So first of all, just some really quick terminology. I personally use the terms model and algorithm interchangeably, but they're actually different. So you might have heard the phrase training a model. That is a lot of what we're going to be doing for this phase, next phase, and actually for the rest of the course. So the difference between a model and an algorithm and why I use them interchangeably is because a model trains via its algorithm. So this is my definition, actually, I think. You can think of an algorithm as a series of steps that a model takes to train. So while the best model for your data is a regression that has this equation, and we'll talk about this more later, but this is basically an equation for a linear regression where y is your predicted value, the x's are the variables that you're using, and the betas are your parameters or coefficients. The algorithm is the process of choosing the right values for your parameters. So whenever you're training an algorithm or training a model, what we're trying to do is find optimal parameters. So in the context of statistical learning, there's two main types of data, and we'll be using these terms a lot over the rest of this phase. We have dependent variables and independent variables. So there are a lot of different synonyms for these. Dependent variables, basically data that can be controlled directly. For our purposes, they can be called outcome variables, target variables, response variables, and also independent variables, which are data that cannot be controlled directly. So these are predictors, inputs, features, explanatory variables. So in our models, independents affect the dependents. So conventionally, the independent always goes on the x-axis, and the dependent variable always comes on the y-axis. This is not something that we talked about last phase when we were doing visualizations, but from now going on forward, if your visualization has the context of, something predicting something, what you're predicting should always be on the y-axis. That's just visualization, what's the word? It's just a rule of visualizations. So in this example, you can see that we want to study if age has some effect on annual income. We have some data here. This is just a plain scatter plot. You can see what we're trying to predict is annual income, and this is on the y-axis. And age, or whatever variable you're trying to predict income with, will be on the x-axis. So these are just like terminology things. Questions so far? Awesome. Okay, so we're finally going to get into linear regression. So a statistical model defines a relationship between a dependent and an independent variable. So a linear regression is a type of statistical model. We'll actually talk about a few others next phase. But this linear regression shows the relationship between, as I mentioned, dependent and independent variable. In this graph, we can see that the relationship between age and income can be shown using a straight line that connects the individual observations in the data. So the line is our model. So as I mentioned earlier here, the model has this equation, which is our line. So our line has this model. So our line is this model. Again, to break down what this equation is, here we have y, the predicted value. So y is our income. Next, x is usually our variable, our independent variable age. And here, beta 0 and beta 1, you might see them as other letters. I think some places use the letters M, but these are our parameters. In the context of a linear regression, and we'll talk about this a little more in depth as we go through the study group. In the context of linear regression, our parameters are coefficients. So the one that doesn't have an x value with it is our intercept. And again, we'll talk about graphically what that means. But anything that's with an x is the coefficient of the x that it's with. Questions about this part? Nice. All right, so how do we decide what the best line is, right? Given this data and given like no math at all, we can draw a bunch of different lines that seemingly fit through all of these data points. But there is a way to decide what the best line is. So we're gonna talk about that. So actually at the start of next phase, we're gonna talk more about machine learning and how that works. But in every machine learning model, and this is actually a machine learning model as well, with every machine learning model, there's an associated cost function. I don't think I use the word cost function here. Oh, actually I do, nice. The cost function basically measures error in your model, or is some metric you can use to improve the fit of your model. And in a linear regression, it is decided that the cost function in a linear regression is the sum of squared residuals. So for this model, the best fit line is the line that gives you the smallest sum of square residuals. So what sum of square residuals means is all of these red lines, basically the difference between the point and the line, the difference, basically the length of the line squared, and the squaring basically, on one hand, the squaring helps gives you bigger error values if you have like big outlier errors, but also the square takes care of negative values. So squared errors, and the best line has the overall smallest sum of squared errors. We'll talk about this a little bit more at the start of next phase when we're talking about like gradient descent and how, you know, cost functions are optimized. But for now, just know that whatever this best fit line is the line that results in the smallest sum of squared errors. Questions about this?
In the context, when it says that residuals, it means the summation of all these vertical lines?
Mm-hmm, that's right. So these like different y's are something that is something to get used to. To explain this formula here, every yi with no like other symbol, every y actually just refers to the y value of the actual data point. So actually, let me draw this out. For yi, oops, I did not mean to do that. For every yi, yi refers to these values. So these y values of these data points. For anything with a hat on it, and we actually call that a hat, that little like triangle thing on top of a letter. So every y hat is actually the corresponding prediction. So the corresponding prediction, which I'll do in blue, is this y value here, these y values here. And so to find the sum of squared residuals, all of these y's have values on the y-axis. So what you will do is compute for this higher point, compute this difference, compute that difference, square it, compute this difference as well, square it, add it up, and that will be your sum of squared residuals.
Thank you.
You're welcome.
What would be the formula for getting that line, for actually getting that line?
There is a bunch of formulas. There's actually multiple different ways to get to this best line. I believe, I'm actually not going to walk through the exact math, but it uses some form of, so one of the, I know one of the ways to get that best line uses like the correlation between two variables. One of the methods, I think the one that's outlined in your lessons, takes some, it's like a formula that combines like the mean of all your y's and x's and has you compute that. I will say it's not important to know all of the formulas to arrive at this line. There are formulas that exist. I'm actually going to walk through one of them at the start of next phase because there's a linear algebra way to solve this formula, solve for this best line. But we're not going to talk about that now. If you're interested in like the formulas for that, I believe one of the first labs in 18 will go through the exact formulas for finding the best values for beta 0 and beta 1, which will make up this line.
Thank you. Perfect.
You're welcome. All right. Anything else? Cool. All right. So given that we have like this best fitting line, we also can determine how well fit our best fit line is. So the best fit gives you some like value of error, and depending on context, the number can be very big or very small. I think if for those of you who saw the presentations, they were actually predicting housing prices, which preview your project will also be predicting housing prices. They were getting errors of about like 150,000, which like per house and on average, that's like a decent, okay error. But if you're predicting something on a smaller scale, like, I don't know, if you're later we'll look at weight and height. If you're predicting something with an error of, let's see, weight, like maybe like 5 pounds off, that's a pretty good prediction. So it does depend on context, what kind of sum of square residual numbers are good. So something that is more on a level playing field, how well fit is the best fit? This is a number that is given to you about your model between 0 and 1. The R squared tells you how well your line fits your training data. As a really quick overview, in the lessons, it goes through the steps of determining this R squared and the formula of that. Good to go through just to see what it really is. I think that's one of the ones that the math does make sense. But overall, what the R squared is, it is a comparison of how well the model is doing compared to the benchmark. So as you can see here, and here there's a new Y that we'll talk about. Here we have this orange line, and the orange line happens to be the average value of all of these data points. So if you imagine you don't currently have a model, you need some sort of baseline to compare your model to. And usually for a baseline, it's a sucky model. And so the sucky model that we're going to use first is just, all right, we'll just predict everything to be the average. If we have no math to go off of, we're going to just start with, all right, let's just predict the average. That's a pretty safe prediction. And in this case, it's usually the mean. So every time you see a Y bar, which is actually quite similar to the stuff that we were doing in stats, every time you see something with a bar on top of it, usually means the average or the mean more specifically. So the calculation of R squared, just to quickly summarize, is a fraction. It's actually a proportion. And you can see here, we're dividing by the sum of squared between each point and this average line. So you imagine, just to compare the two lines, the average error between each data point and a horizontal line is going to be much bigger than the average error between each point and, you know, a fitted line. And so they take that error as a fraction, and that's how R squared is computed. So usually if you have a higher R squared, that just means that in comparison to, you know, this baseline, your model fits a lot better. Cool. Or you can also say that it fits the data a lot better than this horizontal line. If you get an R squared of 1, which is perfect R squared, it means that all your data points lie perfectly along your best fit line. Questions about this? All right, so these are the main parts of a regression, and we're going to start with just one variable regression today. I'll talk a little bit more about how it expands to multiple regression, which we'll talk about on Tuesday, but a lot of the concepts stay the same. It's just more variables. So, all right, R squared has a formal definition, and I really hope to see in your project presentations that you use the formal definition of an R squared when you're interpreting it. So the R squared value of, for example, 0.85 has a definition of 85% of the variations in the dependent variable are explained by the independent variable in our model. This is not a definition that rolls off the tongue. I definitely agree with that. But it's a really good one to remember, because with any linear regression model, you are going to be made to interpret your R squared values. Questions about this?
Do you get a different R squared for each variable if you're doing a multiple regression?
So R squared is actually computed on a model level. So if you have multiple regression, you'll still get 1 R squared for your entire model for all the independent variables combined. Anything else? Awesome. All right, so let's just start coding, and then we'll dissect the results of our first regression. For regression, there are actually 2 different libraries that you can do linear regression with. First, we'll talk about stats models, which is the one that gives you this, this output that we've seen a bunch. But there's also another library called Scikit-Learn, which I'll introduce on Tuesday. And they both have different pros and cons, and they both have different functionalities, which is why for your project, you very likely will end up using a combination of both. So for our first regression, the data we're going to use is height and weight. So this is just a really small data set. Oops, I need to run this first. It's a really small data set. I think it's just 20 points, and here we have the scatter plot of that. And this is our data, and we want to build a model that can predict weight using height. Gotcha? All right, so given that we want to build this model, what are the steps in the code? There's always a formula step, and you might see this being built in different ways, but just so y'all know, this kind of syntax with like the squiggly line in a string, this is actually the syntax used in R. It's the syntax used in the programming language R. So if anyone's interested and like wondering why that's the case, that's why. The reason why stats models decided to use R syntax, I don't know. But if anyone's wondering like why this weird string, it's because it's R syntax. With the model, how it works is first you instantiate the model. So you're telling it to fit an OLS model, and OLS actually stands for ordinary least squares. And ordinary least squares is what we're doing when we're fitting a linear regression. And least squares basically comes from the fact that when we're fitting a model, we want our squared errors to be the least. And that's where the name OLS comes from. So with that, we have to feed it in this formula so it knows which variable to use as the dependent and the independent variable. This basically means we're predicting weight with height. So weight is predicted by tilde height. When you have multiple variables, you'll just add the other variable names to the end of height. So if you're doing height plus age, it will be that format. And that we'll talk about more on Tuesday. This actually very conveniently pulls out column names. So these are actually the column names from the data frame. So that's another like kind of convenient thing as well. If you only want to like test certain columns, you can just change the formula instead of changing your entire data frame. So once you have this OLS set up, you just have to call .fit. And the .fit is the method that is fitting your best fit line, that is fitting your regression line. So once you set up your model, model itself actually has a lot of different methods and attributes built into it, one of which is the summary table. So with this summary table, this is what you'll be interpreting a lot of. Before I get into interpretation of this, any questions?
How would you get the line on a graph?
Ooh, getting the line. Gotcha. So you mean after you fit the model, how would you visualize the line?
Yeah.
This is something that you can do after the fit model. I'm not sure if I have it here actually, but I think I can live code it later. So we'll try after this. But yeah, you basically will plug in your values and it'll plot the line on Matplotlib, which I will try. I'll attempt later on. But yeah, that's a good one. I believe the code is also in some of the lessons, but I'll do it anyways. Any other questions before I get into interpreting this output? All right. I think this is the main thing that you'll be looking at when you're doing a bunch of linear regressions. I'm going to circle the main things that you're going to want to look at. First off, R squared, as I mentioned, R squared is really important. With R squared, you also see an adjusted R squared. Adjusted R squared is because adjusted R squared comes into play when you have more and more variables. And so this is when you're doing a multiple linear regression, which is what we'll be talking about on Tuesday. Basically, there is a trend that as you have more variables in your regression, your R squared will inevitably go up. That's just because of the math of calculating R squared. If you have more dimensions, is just the way that the R squared value goes. So adjusted R squared tries to take into account the number of variables that you're using, just because naturally R squared will go up if you add more variables. So that's what adjusted R squared is. Another main thing we're going to be looking at is the coefficient. So coefficient is our beta 0 and beta 1. Those are the parameters of our model that we are trying to find here. And I'll go into each one a little bit in more detail after I like talk about which ones are important. And then also the last one would be p-value. And p-value, once you see a p-value, means that there is some sort of statistical testing going on. And we'll talk about that statistical test right after we talk about all of these numbers. With the statistical test, you might want to look at the t-statistic, but the t-statistic is the one that leads to the p-value. So this p-value is the probability of the t-statistic. And then there are these confidence intervals here, a little bit less important, but these confidence intervals are the confidence intervals for your coefficients. So if actually you were to take these coefficients, this standard error, and plug it into the confidence interval formula, you'll end up with these confidence intervals. But usually for our purposes of modeling, confidence interval a little bit less important. Finally, other things that might be interesting to look at, probability of F statistic. So we talked a little bit about F statistic when we talked about ANOVA. It has a very, very complicated formula, so I wouldn't worry about that too much. But you can sort of think about F statistic in this situation as like an overall T statistic for your entire model. So each of these parameters here has a T statistic for individual parameters, but the F statistic you can sort of think of as like an overall statistic. And then the probability of F statistic is the p-value for that F statistic. And just because of the nature of like, you know, this F statistic being an overall stat, usually this probability will always be very, very small. So here you can already see that's negative 10 to the power of negative 13. So because of that, if you see a number greater than 0.05, which you very rarely will, if you see a number greater than that, then there's something very wrong in your model. And then you have to probably rethink how your model is constructed. There are all these other numbers that are, I mean, useful, but a little bit less important. I I have actually copied over here just so you, I don't know if you happen to use this notebook more. This is actually copied from one of the lessons, but this goes through the, this basically is the interpretation for every single thing in this output. But again, the most important ones are R squared, p-values, and coefficients. Questions so far? We'll talk about what this p-value is testing for right after this.
Why is our confidence interval is negative?
So here is because our intercept is negative. So they're saying that like the interval of negative 0.244 and negative 0.164, that's the confidence interval that contains our parameter value.
Okay. And a standard error is our residual, or?
So the standard error is the standard error for the parameter. So the standard error is the possible error in calculating this coefficient.
Oh, okay.
Mm-hmm. Yeah. Typically, we don't really interpret standard error and these confidence intervals that much, because the information that we need is whether the coefficient has a low or high p-value, and that sort of takes care of that. Yeah. Let me see. Anything else?
Yeah, the confidence looks like it's based on 95% confidence. Is that always, or can you change that?
I actually have never tried to change it. I honestly don't know if you can. I would assume that you probably can, but I've never tried. I actually don't know if you can change it. I'm curious.
I'm pretty sure you can. I read it in one of the labs, but I didn't try it out.
Yeah? Okay. So let's just take a quick look and see if you can change your, so this is quarks. So yeah, it's probably somewhere there. I wouldn't be surprised. But yes, it's probably in the dot fit, but yes, it makes sense that you'll be able to change that. But for our purposes, because we're doing very general linear regressions, we probably don't have to. I would say like only in the future when your job needs you to do linear regressions, that's when you maybe might want to do that. But I mean, the confidence intervals are also like directly derived from these. So yeah, sorry. I mean, your T statistic, never mind. I'm not gonna go into that, but yeah. All right. So really quickly, what is this hypothesis test? What are we testing for here? Like, what does this T statistic, what is it derived from? What are these p-values confirming? So the hypothesis testing in regression is testing for a relationship between your independent variable with your dependent variable. So your null hypothesis is that there is no relationship between independent and dependent variable. And you're testing an individual hypothesis for each independent variable. It's kind of a weird way of thinking it, but you're testing them individually, but you're still modeling them all together. I think we can discuss that a little bit more when we get to multiple regression. But the null hypothesis is that there is no relationship between the independent variable and the dependent variable. And to contrast that, the alternative hypothesis is that there is some relationship between independent and dependent variable. So if we reject the null hypothesis, which is if we have a p-value lower than 0.05, it means that we believe that there is some sort of relationship. Cool? So if we fail to reject null hypothesis, that's just the opposite. We believe that there's no significant relationship between dependent and independent, and that our slope parameter is not significantly different from 0. And so here's where we bring in the numbers. For no relationship, and we sort of talked about this at the very beginning when we talked about like correlation. If you have a correlation of 0, it means that there is no relationship. Once you have some sort of, so there's a slight difference between correlation and also coefficient. But in this case, having your coefficient as 0 means that there is no significant relationship. What is kind of confusing is that sometimes these coefficients can be very, very small numbers, very close to 0. So for example, I mean, 5 is, I mean, depends on context, but let's say you get a coefficient of 0.01. That doesn't mean that there is some weak relationship, because you can have a coefficient of 0.01 and have a p-value of 0, and that doesn't mean you have a weak relationship. That just means that you definitely have a relationship of 0.01. So that also comes to how we interpret coefficients, which I do want to talk about right after we finish talking about hypothesis testing. But does anyone have anything to clarify about these hypotheses?
If it's not statistically significant, would we want to remove that variable from the model, or should we just leave it in and
Absolutely.
say
So, yeah, you're on the right track. One thing to do, honestly, sometimes the simplest thing to do is just remove the variable. But tomorrow we'll talk about different things that you can do to maybe transform your variable or change it a little bit such that we can still keep it in some form. But yeah, you definitely, in your final models, you don't want to see high p-values, because that just means that you're including variables that are not significant.
Thank you.
You're welcome.
I had a question about intercept. What does intercept really mean? I get that height is one of our independent variables, right? Height is the independent variable. And then what is the intercept?
Yeah, I want to talk about the intercept after we're done talking about p-value, but I am about to talk about that.
Okay.
Thanks, Mark. All right, any last things about like the hypothesis here? Cool. This is just a reminder of what p-value is. Basically, if you have a p-value of, let's see what it says here. If you have a p-value of lower than 0.05, the p-value means that it's a probability that the coefficient is actually 0. So basically, if your p-value is high, there is a pretty high chance that your coefficient is actually 0. So there's a pretty high chance that you have no significant relationship between your independent and dependent variable. Questions on that? Every time I have like large chunks of text, I am bad at reading. All right, okay, so now we're gonna talk about the coefficients real quick. So here what I'm gonna do is I'm gonna sort of draw out what's happening in a linear regression. That is not what I wanted to do. Where's the straight line? All right, here we go. So what we're doing in a regression, and let me actually undo this and do it here. In a linear regression, we're trying to define some sort of relationship between independent and dependent variables. More specifically, we're actually trying to define a linear relationship between dependent and independent variables. So first off, with height. The coefficient of height being 5.539 means that with every 1 inch increase in height, you have a 5.539 increase in your weight. That's exactly how you would interpret that coefficient. Again, it depends on like what are the variables and what their units are. I know for this data set, they actually didn't specify, but I'm just gonna assume that this coefficient basically means for every 1 unit increase in height, in this case 1 inch increase in height, weight will go up by 5.539. So that's just like the relative change every time you go up by like 1 unit. You don't know where your starting point is, but you know that if you are 1 inch higher, 1 inch taller, your weight will be 5.539 pounds heavier. And so the intercept sort of gives you a starting point. Your intercept, I know it's a little bit abstract here, but your intercept is basically what your weight value is if all of your other variables are set to 0. And I think once I draw it on the graph, it might make a little bit more sense. But the intercept of negative 204 is saying that if your height is 0, you actually start with a weight of negative 204. So what that looks like, this x-axis is going to be weight. This x-axis is going to be height. And let me just draw that super quick. This is height, and this is weight, and these are our axes. With a linear regression, we're trying to plot a straight line. And this actually is our formula for a straight line. So if I were to draw it super quickly, this is what our line will look like. This point where it cuts the weight axis, that is your intercept. So this point over here is actually -204. And then as our height increases, our weight increases. And if anyone remembers like calculus, the slope of this line is the coefficient. So this slope is 5.539. So that means that at like a height of, for example, let's see, to find the height at this point here, let's say we want to find the height here, what we would do is we would draw a line up here and see what its weight value is. And that's exactly how we're making predictions. Questions about that? I know the intercept thing is a little bit abstract, but it kind of makes sense. Only up till like a certain height can you start to define like a positive relationship with weight. So I think given these numbers, you'll have to get to about like 40 inches. I think this number will roughly be about 40 inches to start incrementing your weight for it to like make sense with the relationship in the data that you have later on. Because I don't think there are many people who are below, what, 40 inches is like less than about 3 feet. I don't know, but yeah, I'm sure these are adults. So yeah. Questions about this?
Reason why the intercept is negative is because there's just no data for people shorter than that or shorter than that amount.
That is sort of like an auxiliary reason. Because we want to, so this line basically means that our data was around, let me see if I can plot this. Given this line, we can sort of see that our data was like kind of around here, right? And because we want to form a straight line that goes through this data perfectly, it just so happens that the straight line that goes through this data perfectly happens to get to some negative. If by chance, let's say, for example, instead of those data points, we had data points that looked something like this, and of course, different contexts. If for some reason we have data that look like that, then it's possible, then we would definitely have like a positive slope, positive intercept. So it really just depends on like where the bulk of your data is, how the data is sort of like arranged in space, that it just so happens that wherever it cuts the dependent axis at 0, that's just the intercept term. So
my question is, why would we extend the line? Why can't the line stop where the data begins? Because, like, for example, in our example with the weight and the height, it doesn't really make sense to go lower than the points. It's not really so accurate. So
absolutely. Yeah, we can totally stop the line here. Like, we don't have to plot that line after this point here. We can definitely not plot it, but it's just the way that mathematically the linear regression works. It needs to have some starting point at height equals to 0 and then start adding there. So yeah, I mean, this part down here doesn't make any sense. Like, it's not possible to have a negative weight. So it's just that, because we want to fit a linear relationship, and the linear relationship happens to only be positive from, for example, like 40 inches. Below 40 inches, you can say that, yeah, the predictions will not make any sense. But per some chance, let's say we have someone who is like 30 inches tall. Like, let's say we have like a child that's like 30 inches tall and want to measure their weight. This model will not be accurate. We would just have to like refit a model.
Yes, someone has to like look at the context of the data before
Definitely. Yeah, context is very, very important with modeling. But yeah, I know the intercept term is a little bit abstract to think about, but that's sort of like how the formula works, because especially when we had talked about the formula of a linear regression having this form of y equals to beta 0 plus, and that's 0, there we go, plus beta 1 x1. We can basically come up with any weight value by taking beta 0 being the intercept minus 204. I should be typing this out, that would be easier, but whatever, plus 5.5 multiplied by height. So that means given any height, this is what our model would predict as weight. Cool. All right, that's just how the model works, that we end up with this negative intercept. But usually for linear regression models, the intercept term is not something that we interpret with context very often.
Yeah, it makes more sense in this way, because if we want to calculate the beta 0 on the other side of the equation, so our dependent variable minus the beta 1 and multiplied by the independent variable, it makes sense. Yeah, it becomes negative.
Yeah, so if we were to just like rearrange this, let's see, there's no good like rearranging formula, but yeah, if we want to like find what our beta 0 is, we can just rearrange it by taking y minus b1 x1, which I think might be one of the formulas that is outlined in the lessons as like a way of calculating this line. All right, let's move on from this, unless there are any other questions. All right, so two purposes of modeling that I outlined at the very start. First is to construct a model that can help us draw conclusions about our data. So from that model, we have determined that there is a relationship between weight and height, and that the relationship is that with every increase in 1 inch of your height, your weight goes up by 5.53. The other purpose of your model is to make predictions. So most people, or a bunch of people, create models just so that they can make predictions on data that they don't have. So let's say, for this example, I know it's kind of silly, but let's say we want to predict the height, predict the weight of people. Let's say we don't have a weighing scale, but we have a ruler. So we want to predict their height. And we do have the weight data of these 20 people. How are we able to see how well our model works at predicting predicting the weight of people whose height we have, but weight we don't have? I don't know if I said too many words, but let me just say that again. We want to just see how well our model works on predicting unseen data, because that's usually what we're modeling for. We're modeling such that, we take this training data, we model it such that we can make predictions about things that are happening in the future, for example. So here, this is actually outlined more so in topic 19, but I do think it is worthwhile talking about here. Usually what we do in practice is we actually segment our data. We do a random split of our data, and we train our data and we train our model on one set of data, and we test our model on another set of data. And so the model is being trained on our training data. It has no information on like our test set. And then after we've trained this model, we can actually compare the results in our test set to see how well our model is at predicting things that it hasn't seen before. And we'll walk through this example to illustrate that. So I had mentioned earlier that another library that also does linear regression is Scikit-Learn. Scikit-Learn is going to be the library that we use for all of phase 3 as well. So meet Scikit-Learn, everybody. What we have here is this method called train test split. And what train test split does is it takes your data and randomly splits it into a train set and a test set. Here you can actually set your test size typically, you train on 80% and test on 20%, depending on how much data you have, or maybe if you want to just have more testing data, you might change those proportions up. But typically, your test size is 20%. Random state is something that I believe that we have talked about a little bit with like the sampling that we did in stats earlier, but this random state just means that for any train test split in this notebook, if you give the same random state, you're gonna split it the same way. And it's just good for reproducing results and to just make sure that you're testing it consistently. So what we do here is first we train our model only on the train set. So I made one very minor change here. Instead of training on our full data frame, we're only going to train on the train set. So what you see here is with this train test split, it just splits it into train and test. We can actually take a quick look. Train, oops, I have to run this. Train looks like this, and it's all scrambled up because it's randomized. And train should have 16 rows because test has 4 rows in this case, because our data set here is only 20 rows. So what we do here is we're going to train our model only on the train set. And so we're only going to train it on 16 items. So once we do that, you can see that our values are a little bit different. They're kind of similar depending on scale, but our intercept went up from -204 to -200. Here, our coefficient is slightly different. Our R-squared has also gotten higher. So this model was built without any information from our test set. So that means we can be fully confident in whatever, we can compare the results of the predictions on the test set to see how well it actually does at predicting. What I mean by that is we can test our model using the test set. So after you've built the model, as I mentioned, model.summary is one of the methods built into the model. Another method built onto the model is .predict, and .predict is especially useful because it literally does the predictions for you. So what you see here is you do .predict on the test set, and this test set is this set here, and it automatically knows to pull out only the height, plug in that height into the formula, and return predicted values for weight. So these are our predicted values for weight. And if we just take a look at weight here, these are the actual values for weight. So you can see that they're actually not exactly the same as expected because your points never fit perfectly on the line. But you can see that they're kind of similar. You can see that here for this particular point, it was predicted 172. Here, the actual value was 165. And so this is another place where you can compare your error values.
Basically, right now, all it's doing is just plugging in a linear equation. It's just plugging in the x and getting the y.
Yeah, absolutely. The formula that I wrote out earlier, it's literally just plugging in the value for height and giving you the value for weight.
That's once you get the line, right?
Yep, this is after you get the line. Yes. And what we want to do here is look at how off our predictions are. And so here what we're going to use, you can actually compute it using NumPy as well, but there's a built-in mean squared error function in Scikit-Learn. Typically what we do here, if you remember what I talked about earlier, y hat is usually any prediction. So here, this is actually the same output. I took model.predict test, assign that to y hat. And then I just took my y test and assign this particular series to y test, and I can actually compute the mean squared error between the two. So this this formula works by just taking in 2 arguments of your hat and your y test. They actually have to be the same length, and they'll compute the error between them. So running this, our mean squared error is about 78 pounds. And so our root mean squared error, which is a little bit more comparable on our scale, is 8.8. So basically what we can say is on unseen data, our model predicts around 9 pounds off. And so that's also another useful metric that you can use to evaluate your model. Questions on this? All right, and I actually forgot that I had this here. Could have used this earlier, but here I'm actually, this is a formula that I used, that I wrote to predict weight using any height. So I just took the coefficients from the model output that we saw earlier. And actually I shouldn't be using these coefficients. I should be using the train set coefficients, but same thing. What we can do here is this function will take in any number as height and give you a prediction for weight. So I can change these numbers. You can see like 100, you get that weight. You can actually take a look at those really short people, which will get wrong information of like negative pounds if you have under, I think like under 40. I don't know what the number is, but yeah. Basically, this is the function that results from the model that you trained. Questions about anything we've talked about so far?
Yeah, the training step, would you do that multiple times so it would be different subsets of your data being trained?
That's a really, really good question. Yes, but that is not something that you do all the time. Doing different kinds of train test split across your data set is known as cross-validation. And cross-validation is actually something that is in topic 19. Cross-validation, what it does is, for example, in this case, we did just an 80-20 split. With cross-validation, you can actually divide your data into, for example, divide your data into 5 parts. And what it's going to do is it's going to run your model 5 different times with 4 parts as the train set, 1 part as a test set, and keep changing which one is the test set, just to like run your model over different steps, different subsets to see if your model still holds. And that's something that we'll talk about more on Tuesday. And doing something like that just makes sure that, you know, maybe by chance, by like randomness of train test split, maybe all like the super tall people were in the training set and not in the testing set. And so when you test, the model were like overfit to like a specific subset of people that gives you more inaccurate predictions in your when you use your test set. We'll talk about that more for sure next week. But yeah, cross-validation, which is doing multiple train test splits, is something that we do as well. Awesome. This last part of this notebook, I wanted to talk about the assumptions for linear regression. I'm sure some of you saw like a bunch of these funky plots during those presentations, so I wanted to talk about why those are important. So regression is a parametric technique, which means that it uses parameters that's learned from the data. So it's actually learning what the best intercept and what the best slope is for the line. Because of that, certain assumptions must be made. So there are certain conditions that have to be met for your linear regression to be like reliable or working the right way. Very often you can have a model that, you know, has a great R-squared, has very low p-values, has a pretty decent RMSE, and that could honestly happen by chance. But you also have to check for the assumptions. There are 3 main assumptions that we're going to talk about today. There's one more that comes into play with multiple regression. But these assumptions are important to check because it just says that, you know, you're using the linear regression the right way. Usually, if your linear regression assumptions are not fulfilled, it usually means that the data and the specific feature set that you're using is not best suited for a linear regression. And so a very common, a more common conclusion of that, I don't know if y'all saw in the presentations, is that a linear regression might not be the best model for your data. So these are all things that in your projects you will have to check for at certain points. So there are 3 main assumptions with simple linear regression. All of these assumptions do carry forward to multiple regression. So the first assumption is linearity. First of all, the linearity assumption requires that there is a linear relationship between the response variable and the predictor. So basically what you would do in this case is you would plot like a scatter plot of every single variable, every single independent variable against your target variable, and just taking a look at that. And as long as they're fairly linear, that assumption is fulfilled. So test it with scatter plots. There we go. What you would do if you have a nonlinear relationship, we'll actually talk about that in topic 20. Also important to check for outliers, because outliers can skew your model. The next assumption is normality. So one assumption of your linear model is that the model's residuals should follow a normal distribution. And so these are histograms of residuals. Usually you don't have these exact plots, but usually you have QQ plots. The interpretation for QQ plots, I honestly never remember. Every time I have a QQ plot, I literally look up QQ plot interpretations and I just see which one mine looks like and interpret it that way. But basically you want to have your residuals normally distributed. This QQ plot is a very, very similar test to the Kolmogorov-Smirnov test that we talked about 2 study groups ago. Just so you'll know, it's also a test for normality. Really quickly, what does normally distributed residuals mean? So if we have this line here, and I know I talked about plotting this residual line. I think Joey had asked about that. I will instead find which lesson has it and send it out. But all right, if you have this regression and you have like a regression line that goes through it like this, ideally what you want is for your residuals to be normally distributed, centered around 0. So you want majority of your points to have small residuals, and then, you know, as you move away from the line, fewer residuals. So what that means is, if I were to draw like the normal distribution line, it should look somewhat like this. More points close to the line, and then as we get further away from the line, fewer points out here. And then imagine this normal distribution curve across the line like that. Does that make sense in terms of like normally distributed residuals? Basically, if you have something that is skewed, if it's not normal, like for example, you know, you have more points up here compared to the other side, that basically means that your line is not fitting very well. All right, one last assumption to end off, homoscedasticity. And homoscedasticity basically stands for equal variance. So this is, again, all your residuals. What you're looking for in a residual plot, and a residual plot is this plot right here, is that you want to see that the variance of your residuals is constant across your variable. So here you can see that this is height here, and these are your residuals. This, because there are so few data points, not as clear, but ideally you want to see all of your points looking sort of like here, like pretty evenly around this horizontal line. Other cases of what can happen is you have heteroscedasticity, which is uneven variance. When you have heteroscedasticity, and I'll sort of like illustrate it over here, if I have points that, or residual plots that look like this, what that means is over here for like the 58 through like 64 region, my model is pretty good at predicting because all of the residuals, all of the errors are pretty small. But then as we get to like greater heights, your model loses predictivity. So that just means that if you have heteroscedastic residual plots, that means that your model is not consistently good at predicting across the board. So that's why homoscedasticity is something else to look for. Questions about that? Awesome. I know that especially for those of you who haven't looked at this material yet, this was a lot of new stuff. Hopefully, you know, the fact that I sort of split up the study groups across the weeks, it does give it more time to sink in, I hope. And when we talk about multiple regression on Tuesday, a lot of these concepts will come back. final call for questions. All right, things that I know I need to look out for is like plotting that line. I will also send out that like book of statistical learning that explains stuff like this. A little bit in depth, but really well in my opinion. StatQuest also has a bunch of great great videos on linear regression if anyone likes that guy. All right, final call for questions. Cool. Well, let me stop this recording real quick.